This slide conveys our focus areas in the rail industry. Our customer base includes rail operators, rail infrastructure managers, train manufacturers, and system suppliers. We work with rail operators and infrastructure managers to design and develop solutions to automate asset inspection and maintenance. We also work heavily with train manufacturers in the design and development of autonomous systems as we leverage technologies for object detection, sensor fusion, perception system development. We have deep experience in developing safety critical systems for system suppliers supporting projects up to SIL4 level rigor, including cybersecurity requirements. We also work heavily with train manufacturers and system suppliers where we leverage our mature model-based system engineering approaches to product development. For passenger rail operations, our focus is on digital solutions to improve passenger convenience and safety. And lastly, we also focus on IoT and cloud advisory services when it comes to asset management and also for predictive maintenance for our customers. In this webinar, our focus is going to be for rail asset inspection and maintenance. In this slide, we see the scenarios where the parts are missing or damaged or loose. Typically, it is a visual inspection to check whether these are in order. In some cases, vibrations generated by the wheel track interactions could also be used for certain conditions. Many of these scenarios shown in the next few slides are typically visual inspection based. In this slide, we are seeing scenarios where we are interested in determining various damages to rail, whether there are cracks in the joint assembly and the rail, whether there are damages in the frogs and guardrails. In this slide, we look for the need to measure some geometrical parameters such as curvature, cross level, gauge of the rail track, the gaps, the misalignments in the various geometrical assemblies. In these scenarios, additional to visual inspection, measurement needs to be done as well as part of the solution. In this slide, we're looking at scenarios pertaining to ballast, like the profile of the ballast, whether there is a washout in the ballast, etc. Whether there is an excessive ballast, or if there are ballast which is overlapping and is occupying, is sitting on top of the cross ties. Now, this could also include other scenarios such as checking for if there is waterlogging next to the tracks, right? And especially for ballast, it is also about assessing the profile of the ballast, not just whether the ballast is there or not, but also checking for the profile, which is important for railroads. In this slide, we see scenarios for detection of vegetation in the rail track, as well as the overhead vegetation, which can interfere with the rail movement. And whether there are objects on the rail track, maybe some rocks or maybe some sort of a tree or something which has fallen on it. It could also include checking for the condition of the signages, which is there next to the tracks, as well as signal post and structural monitoring of the various civil structures, especially the bridges and tunnels, which are there along the route network. Rail infrastructure owners are also interested in monitoring soil moisture movement, especially in mountainous regions, to detect if there is soil movement, which could be used to predict a landslide. In this slide, I would like to introduce our innovative development platform called Inspect at Scale, which we have developed for developing asset inspection solutions quickly, thus saving cost and time for development. The smartness in this development platform is the approach we have taken when architecting the development platform itself. Firstly, if you see, almost all physical assets can be monitored using one or more types of sensors. The sensors includes, but not limited to, cameras, LiDAR, ultrasonic sensors, IMUs, pressure sensors, to name a few. In addition to the raw data from the sensors, the other key part in developing an inspection solution is the data processing algorithms, the various machine learning models, the various functionalities which does the decision making, the data analysis on the raw data. What we have done is to bring these two elements of a solution together in a very easy to use UI with workflow orchestration to rapidly design, develop, and simulate asset inspection solutions. The platform, what we have, provides a lot of capabilities, which I will elaborate right now. The platform provides a variety of sensors to choose from the list. So we already have a lot of sensors which have been added into the platform, and as and when more sensors are available in the market, the plan is to add them into the list. Now, depending on the problem to be solved, a solution developer can pick one or more sensors required for inspection of an asset. For example, if the problem to be solved is to detect breakages in the cross tie, then the top view of the cross tie taken from a camera is good enough as a starting point. On the other hand, if the problem to be solved is to check the ballast profile or washout, then in addition to the camera images, LiDAR point cloud data would be useful as well to accurately assess the ballast condition. The solution developer can then create a solution pipeline by using one or more sensors and then choose amongst various existing reusable assets, which could be algorithms, features, libraries, using the UI. In Inspect at Scale platform, we already have various reusable assets which can be used straight away. For example, the platform already has algorithms for collision detection using sensor fusion, for terrain mapping of a 3D environment, localization using existing point cloud data, and many other features. It also has various pre-trained AI/ML models for object detection and classification, which, for example, could be an ML model for detection of a signal lamppost, or an ML model for people detection, or for wheelchair detection, or for rail cross-tie detection. These ML models have already been pre-trained, on a vast amount of data and are thus ready to be used. Inspect at Scale development platform allows solution developers to quickly develop and validate solutions by leveraging existing solution components appropriate for a problem, and then quickly validate it with sample data. The platform also has synthetic scene generator capabilities, which is mentioned as SSG on the slide, which can create synthetic data to generate sufficient data set for AI/ML model training, as well as to validate a developed solution. It is possible to create using synthetic scene generator, for example, a 3D environment with people, object, trees, electrical overhead lines, and other objects around a track, and validate a collision detection solution which you have developed. Similarly, for an image of a rail track, a synthetic scene generator can add different levels of vegetation with different hue and color to validate whether the AI/ML model used for detection of a component is able to handle the variances of the scene, which can happen, from season to season. The grass can be green and in one season, whereas the grass may become brown or dries out, during the summer. But it's the same asset which we want to inspect. As more and more solutions are developed, more and more reusable assets gets developed. This provides the ability to reuse various solution components to further increase the return on investment. In the next slide, I will briefly talk about the various criteria which have to be considered in designing an asset inspection solution. All these solutions are made up of one or more AI/ML models, which is then processed by computer vision algorithms to finally detect an issue or fault, and in some cases, measure the gaps and the distances. Let's go through each one of them in brief. The first one on the top left on the screen is the detection of various defects in cross ties made up of wood and concrete. The breakages, the splitting, and decay were detected using camera images from a drone. We used GAN-based synthetic data generation to create a large variety of training models, training images for training the high-performance AI/ML models. The second one on the top from the left was developed to find problems in anchors, to find missing or corrosive anchors. Here again, synthetic data was created to create larger training set for training high performance AI/ML models. This solution was deployed on the cloud. The third solution on the top is for the detection of spikes and the various possibilities which needs to be detected, such as the number of missing spikes and deformed spikes. We used a CNN-based custom model development for this solution. Now, one of the key things to highlight here is that getting high accuracy of solution requires a well-trained AI/ML model, which in turn requires sufficient data set for training. Getting large amount of data from the real field is not only time consuming, but also practically impossible in many cases or cost prohibitive. But getting data which shows both good condition and bad condition of the assets is important for training high performance AI/ML models. For example, getting images of different types of breakages in a cross tie may not be possible easily. And in these circumstances, using synthetic scene generation is going to be very useful. Now I'm going to show the digital twin development platform called LeXi, which we have developed. And some of the digital twins we have developed using the LeXi as a development platform. This is applicable for any of the onboard systems which is there on a rolling stock. In this section, I'm going to talk about the work we have done using on digital twin solutions. As you know, digital twins already exist in the industry, which could be for creating a digital twin for a system or a process. Tata Elxsi, having worked closely with various customers, we identified that there has to be a better way of developing digital twin, and we conceptualized LeXi for addressing that need. LeXi is a digital twin development platform which can be used to develop digital twins in an easy way with reduced cost and time. The innovative approach in architecting LeXi platform was to look at what all features or development platform will be reusable across digital twins for various systems. And then we developed LeXi with out-of-the-box features to speed up the digital twin development. For example, we decided to use digital twin definition language for describing the models and the interfaces for all the IoT digital twins to reduce the time for creating real-time virtual representations or for realizing virtual descriptions in the physical system. As DTTL is open standard, it becomes easier to integrate external models and maintain the digital twin which you have developed. With LeXi, it is possible to create a hybrid digital twin combining the physical models, which are physics-based, and data models, which is built on top of large amount of data for higher performance of the digital twin for a system. LeXi also has a library of various types of base AI/ML models to choose from for a quick start when developing a digital twin. External models which have been developed outside of LeXi can easily be integrated into LeXi platform using external model adapters, which means you can reuse various models which you have already developed outside of LeXi. LeXi also has out-of-the-box set of APIs for developing various features instead of writing code from scratch. For example, if you want to implement alerts and notifications of a digital twin for a live system, you can easily create it using the API instead of writing code for that. It also has a suite of visualization features with various representations, which enables easy communication of the value of digital twin to stakeholders and see the performance of the digital twin of the system. Various data analytics and prognostics are also available out of the box to develop predictive maintenance solutions. LeXi also provides the framework to create various what-if scenarios for simulation to check the response of the digital twin. These out-of-the-box features enables quick configurations while developing a specific digital twin for a system, reducing the time and effort for coding. Based on our experience, using Lexi as a digital twin platform saves around at least 30% of the cost due to the ability to use various out-of-the-box features. Being built on service-oriented architecture with open standards, modular and cloud agnostic, it is also easily scalable and maintainable.